Hi everyone, welcome back to this session. In this session, I'll be actually walking you through the Excel implementation of the CIR model using the parametric estimation approach, which is the maximum likelihood estimator. See, MLE or maximum likelihood estimator is a statistical method which is used to calibrate the parameters of a model. So in our case, what we are doing is we are trying to calibrate the CIR interest rate model using the MLE method. So if I say MLE or maximum likelihood estimator, it's the same. Okay. So now what is the first thing? See, the first thing is to download the data. Um, I have shown you all how to download the data in the VesiCheck interest rate model video. But if in case, what you can do is go go on this link. Okay, let me open this link. So what is this link? So this link is US Department of the Treasury daily Treasury power yield curve. So what this basically means is the Treasury Department of the US, right? They basically tell what is the interest rate every day. If you see, this is the 1 month interest rate, this is the 2 month interest rate, this is the 3 month interest rate, and this is the 30-year interest rate, right? So what this basically, so you what this US Treasury Department does is they publish what is the interest rate for different maturities, 1 month, 2 month, 3 month, for every day. Every day you'll see this. So what we'll do is we'll download last 1 year of data. Now what you can do is, if you see this website, you can basically use this website to go for different years, and you can download how many years of data you want. You can consider 10 years, 15 years. But in my Excel spreadsheet, just to keep it simple, what I've done is I've just considered 1 year of data. Okay, but just wanted to show you how you can download data. Okay, so basically, if you see, what I've done is downloaded 2024 data and 2023 data. Okay, so our interest is in modeling three month of interest rate. So we are not modeling each interest, each of them. We are just trying to model the 3 month interest rate. Now you might be thinking, why we are just modeling 3 month and why not everything? See, most of the time, if you see interest in this simulation, this interest rate modeling, my let's say if you are doing some pricing of any interest rate derivatives, be it caps or floors, right? Most of the time, they are underlying a 3 month or 1 month. So 3 month or 1 month. So in most of the cases, you will see that the underlyings are 3 month interest rates, and that's where this 3 month modeling, this 3 month interest rate actually becomes very interesting. So even in my use case, I'll do is I'll basically try to simulate the 3 month interest rates. Okay, so we are trying to see how the movement of interest rate will look like. See, the first thing is to get the data, right? As I've shown you, how can we get the data? We can get the data by using the website, which is the US Department Treasury. And if you see, what I've done is I've taken into consideration the last 1 year data. So the if you see, this is actually formatted in this dates are in the US format, which is the first is the month, second this third is the day, and 2024 is the year. This is basically a month, day, and year, right? So this is 3rd of June 2024. So, and this is 1st of June 2023. So if you see, total data points that I've taken is 252, right? If you see on the in the bottom right, the total data points that I've taken is 252. So basically what I'm trying to say is I have considered last 1 year data. Now if you see, this is the data which is 5 point, this is the 3 month data. As I've told you, we are trying to model the 3 month interest rates. Okay, see, the first thing is this is 5.52%. So I thought, let's convert into decimal. See, if I write 5 to 5 5.52%, or if I write 0.0552, it's the same thing. It's the same thing. Why? Because this is, if you divide this by 100, this will give you this value, right? 0.052. Okay, yeah. So we cannot actually, we cannot divide by 100, because, but just think, what is 5.52%? 5.52% is what? Divided by 100. So this is what is 0.052. See, if I write 5.52% or if I write 0.052, it's none of the same. It's the same thing. Okay. These are not different things. Okay. So first thing that I've done is I have taken the actual data, which is just divided this percentage into the decimal form. Okay. Once we do this, once we calculate the decimal, the interest rates in the decimal form, the next component is finding the returns. So how can we calculate the returns of the interest rate? So you always remember the formula for calculating returns is today's interest rate divided by yesterday's interest rate minus 1. So today's interest rate divided by yesterday interest rate minus 1. So if you see, this was my today interest rate, and this is my yesterday's interest rate. Okay, this is my today's interest rate, and this is my yesterday. So what I'm doing is D2, which is this divided by this minus 1. If you see this formula, D2 divided by D3 minus 1. So this divided by this minus 1. So that's how you will calculate the returns for each day, right? This is how you will calculate the returns for each day. So why are we calculating the returns? See, always remember when we have to compute the volatility of the interest rates, right? If you all remember this equation, dRT is equal to A times B minus RT dt plus sigma square root of RT dWT. Now the sigma is what? It's sigma. This is nothing but the volatility of interest rates, right? So now how can we calculate the volatility of interest rates? We do equal to the deviation. Okay, we'll do what? Standard deviation dot sample, and then we'll give these interest rates. We'll give these interest rates to calculate the volatility piece. So that's why the first component, if you see, what we have done is first we have calculated the just converted the 3 month rate into decimal form, and then just calculated the returns, which is today's interest rate divided by yesterday's interest rate minus 1, and then using this we have calculated the standard deviation dot sample. Now you might be thinking, if you see this formula, STD, we have two formula, dot P dot S, standard deviation dot population dot sample. So what is the difference between population and sample? See, population means everything, but we have just considered 1 year data, and that's why we are saying it's a sample. Okay, because we have calculated just 1 year data, and that's why we are saying it's a sample. Okay, and that's why we are using the formula of sample, STDEV, standard deviation dot S. Okay, and we'll just give these returns to get the standard, to get the volatility piece. Now, understand one thing. If you have not seen my theoretical video of Vesicheck interest rate model, in which I have walked through the MLE method, the theoretical piece of MLE method, I highly recommend you to watch that so that this can be easily understood. Okay. So what is this MLE method? So what we do is we have this market data, right? We have this market weights, right? So what we'll do is we see, tell me one thing. This CIR model, if you see the equation DRT, which is the change in interest rates, right? So can you tell me one thing? Are we modeling interest rates or are we modeling change in interest rate? If this equation was just RT is equal to A times B minus RT dt and the rest of the part, then we could have said we are modeling interest rate, but this is DRT. This is the change in interest rates, okay? DRT is what? Change in interest rate. So what we are trying to model is the change in interest rate. So DRT is what? Change in interest rate, so which is RT minus 1, right? So today's interest rate minus yesterday's interest rate, right? Similarly, today's interest rate minus yesterday's interest rate, today's interest rate minus yesterday's interest rate, and so on, and so on, if you see, and so on. Okay, this formula will just use the change in interest rate and go and just drag it down. Now this is Now what we'll do is we'll model the dr using this equation, A times B minus RT dt. See, one thing is which I want all of you to understand is there's two schools of thought. one thought process says that take the complete equation. Okay, take the complete equation, which is a times b minus rt dt plus sigma square root of rt dwt. Okay, but I have also read that when you are calibrating the model using the market data, take just the deterministic part. Just the first part, which is the a times b minus rt dt. Okay, take just the first part. So that's why if you see how am I modeling dr, how am I modeling the drt is change in interest rate using the CIR equation is this O2, which is A. O2 is what? The speed of mean reversion. Okay. A times B minus RT. What is O3? B, long term mean. What is my RT? Interest rate? This. See, tell me one thing. If we are trying to model today's interest rate, if we are trying to model today's interest rate, it is for sure that we do not know what is the interest rate today, right? Basically, what I'm trying to say is this RT term. If you see this equation, this RT term is nothing but previous day's interest rate. Okay, this RT term is nothing but previous this A times B minus RT, which is D3. This is always the previous day interest rate. If you are trying to model today's change in interest rate, will be using yesterday's. Okay, if you are modeling yesterday's change in interest rate, we'll be using day before yesterday and so on. Okay, so always remember what is this equation: A times B minus RT. So O2 is what? Your mean reversion speed. B is what? B is nothing but the long term mean, right? B minus D3 is what? D3 is what? RT, right? Previous day interest rate. This multiplied by dt. O7 is nothing but dt. See, if you see dt is nothing but 1 by 252. Why 252? Because there are total 252 trading days in 1 year. Okay. There are 252 trading days in 1 year. So that's how you will use the CIR equation. As I said, sometimes you can use the complete equation and sometimes you can use just the first part, which is a times b minus rt dt. Most of the times I have read in certain research papers that they have just used this piece, which is a times b minus rt dt, and some of them I have read they have used the complete equation. So actually it depends what do you want to use. But mostly I would say go with this part, which is just the deterministic part or just the first component of the equation. So this is how you basically calculate the change in interest rate using the CIR model. Okay, this is how you will calculate the change in interest rate using the CIR model. Now if you see in a way, what we are trying to do, we are trying to make sure that whatever we see, whatever is the actual change in interest rate, right? What is the actual change? Actual change is nothing but what we calculate using the market data, right? So whatever actual change in interest rate, that should actually, that should, and whatever we are getting through the CIR model, that should align, right? See, that's what is the aim, right? We are trying to simulate the interest rates, right? We are trying to simulate. So how, when during the calibration piece, we need to make sure that the CIR component that we are calculating, or the change in interest rate using the CIR model, that should actually be very close. These values should be very close to what we see here. Okay, these values should be very close to what we see here. So basically, what I'm trying to say is whatever we are interest rate we are trying to what so the 3 month interest rate model through the CIR model should be close to the actual interest rate that we see in the market. Okay, so this is the actual and this is the modeled interest. This is the actual interest rate. Column F is the actual interest rates. Sorry, actual change in interest rate, and column G is nothing but the change in interest rate through the CIR model. Now, what we are trying to do is we are trying to make sure the difference between the two. What is the difference between the two? Okay, so we are checking what is the difference between the two. So we saw, okay, this is the difference. So we basically calculated the difference between the two. Now what we are saying is let's take the normal distribution of this residual. Okay, so let's take the normal distribution of this. So this change, so what is this? This is nothing I can say as the residual, which is the actual interest rate minus the model interest rate, right? This is nothing but the residual, right? This is nothing but the residual. So if you see, what I'm doing is So I'm just saying that use this normal distribution method to make this residual, which is H2. If you see, this is what H2. H2 is nothing but residual. So I'm just saying that so this residual is normally distributed with a mean of 0. So when I say it's a normally distributed with a mean of 0, what do I mean by that? Basically, I'm saying is let's make this residual 0. And that is the aim of it, right? We want that this residual, which is the actual and the modeled interest rate, the difference between both of them should be 0, right? So what we are saying is we are saying that let's assume that this residual follow a normal distribution with a mean of 0, and definitely it will have certain standard deviation. So let's say this is the standard deviation of this model, okay? And cumulative distribution function is false, okay? So that's how you will say that all these residuals are normally distributed with a mean of 0 and certain standard deviation, okay? And certain standard deviation. So that's how you calculate the normal distribution. That's how you calculate. So that's how, if you see, you calculate all over the basically the PDF, okay? The PDF of the residual. Now, once you calculate the PDF of the residual, the next piece is taking the log function. See, taking the log function. So if you see, what I'm doing is I'm just taking the ln of PDF. I'm just considering the ln of PDF. See, now you might be thinking, why are we doing it? Why are we doing it? So see, MLE method, what it says is maximize the likelihood estimator. If you see the definition of MLE, it is nothing but maximizing the likelihood estimator. What does this mean? We are basically maximizing the probability that these values are 0, that the difference between the actual value and the model value is 0. So we are maximizing this probability, okay? But how will we maximize this likelihood estimator? So once we calculate the log distribution, log of the PDF, right? Once we calculate the log of the PDF, we'll just sum all of it. Just calculate the log of the PDF till the end and just take the sum of it. Once you take the sum of it, now the goal is to maximize this value. Now, how will you maximize this value? Because see, if you just see, these values can change, right? See 0.5. Let's take the average. Let's take the average be this. What is B? B is nothing but, if you see, A is what? A is the speed, B is the long-term mean. So I have actually taken the average of our actual interest rates. Okay. And let's see what is the volatility. We all know how can we calculate the volatility, standard deviation, sample, this, sorry, returns, right? Returns. So that's how we calculate A, B, and sigma. But again, these are just some initial guesses. Okay. These are some just initial guesses. We have not calibrated this using the market data. Okay, we have not calibrated this using the market data. Okay, so how will we calibrate this? How will we calibrate this? So what we have to do is, again, remember one thing, that MLE, the full form is maximum likelihood estimator. So the end goal is to maximize the sum in such a way. How would you maximize the sum? By changing these parameter. Just see, now just look at this. Let me keep it 1. If you see, let's keep at 10. Let's keep at 100. Are you seeing this value? Let's keep it as 50. Let's keep this as 1, or not 1, but let's say 0.7 or 0.5. Let's keep it as 0.5 or 0.05. Let's keep it as 0.05. See, these values are changing, right? So what we have to basically do is we have to change A, B, and sigma in such a way. We have to change the A, B, and sigma in such a way that this sum should be maximized. And when it gets maximized, so in Excel, we have this thing called data solver. In the solver, what it will do is it will use various values of this and try to maximize this value. And once we get the maximized value, these components that we get will be called the calibrated components. Okay, so let's take this as 0.5. Let's take this as the average. average of, let's say, the actual, and this is nothing but volatility is nothing but the standard deviation. See, always remember the initial guesses. The initial guesses you give to your data solver should be close to what you see, because if you just give like 111, it won't be that good. When you give 111, it won't be that good. So always make sure the initial guesses that you see give should be very close to what you actually see. So now how will we calibrate the parameters? Data, go in data, go in solver. Now what you have to do in the solver, see, in the solver what you have to do is you have to set this function which is L2. You maximize this value by how? By changing these three parameters. Okay, so what we are saying is let's maximize the value of, let's maximize this value L2 by by changing these three parameters, which is A, B, and sigma, right? A, B, and sigma. So, and what is the subject to the constraint? Tell me one thing. Can A be negative? So if you see this, what I have done is, how will you add constraint? Just click on add. Just click on add, or what you can do is, so keep this value, let's say greater than equal to 0, and just add it. Okay. So if you see, we have added this component, but because I have already done that, let me remove it. Okay. So if you see, what we are trying to do is, we have made sure that A, which is the speed of mean reversion. See, speed cannot be negative. We all know, right? We all drive cars. We all have driven bicycle, motorcycles. Can speed be negative? No, it cannot be negative. It is always positive. So the first constraint is, let the speed be positive. CIR model, as I said, it is used to generate positive interest rate values, and that's why we say that this mean, long-term mean, should be positive. It should be greater than equal to 0. And the last component, which is the volatility, we say that the volatility should be greater than equal to 0. So basically what we are saying is A, B, and sigma, these all components should be positive. And then just click on this, unclick on this, which is, I guess by default you have something like this, but unclick on this and then just solve it. See, as I solved it, I got updated values, right? I got updated values. Now these are my calibrated parameters. See, if you see, my sum earlier was 1100 or something like that, right? But now see, if you remember, let's keep this component. Okay, if you remember, these were was our initial guesses, right? It was giving, sorry, I guess these were our initial guesses, if you all remember, right? Something, we were getting this value, but when we did the solver piece, we got these value, right? So using this value, we what did we do? We maximize this probability. We maximize this sum based not the probability, sorry, we maximize this sum, and that was the aim, right? Maximizing the likelihood estimator. Now if you see the difference between them, the difference is almost zero, almost zero, and it goes in the fourth decimal place. Even if you see the difference, it goes up till the fourth decimal place. So the difference between both of them is very small, very small. If you see, if I just do, if I just plot the graphs, if I just plot the graphs, oops, let me plot it. Okay. I don't know. Yeah, I've recently purchased this Mac, so I'm not very good with using it as of now. But see, the point I'm trying to say is, if you see these two values, these are so nearby. Even the difference it's negligible. It's negligible. So that's what that's what calibration basically means. Or when you calibrate the parameters, that's how you what you're trying to aim is that our actual interest rates and the model interest rates should be very close, and the difference between them should be 0. That's what is our aim. So I hope you understand how to calibrate the parameters of the CIR model. Now we have gotten this value. Now the next piece is to perform simulation. To perform simulation. Okay. So how will we perform simulation? If you see, what we'll do is, see, this 5.0.0552 was the latest value. So now what we'll say is these are the data, historical data points, right? From this day, this is what t equal to 0, right? If you see, this is what t equal to, this date is nothing but t equal to 0, right? This date is nothing but t equal to 0. Now all this date will be the next day of this, right? Right, and so on, right? And so on, right? So basically, I'm just removing this, but I'm just the point I'm trying to make here is this is the last data point that we had. Okay, this is the last data point that we had. This is the last data point we had. Okay. Now the question is, how can we simulate the interest rates using the CIR model? Okay, one more thing I want you to understand is, uh, I know Emily is a method, it's a statistical method. But if you look at the implementation piece, this is how it's been implemented. Now, as I said, you might be thinking, why do we take PDF, or do we take log of transformation of PDF? See, as I said, I'm just trying to make sure you understand this concept because this is very important. We are trying to say that this residual, which is nothing but the difference between the actual interest rate and the model interest rate using the CIR model, right? So just let me update the CIR. Okay. So this RT, so this, if you see, this is nothing but your column F, and this is nothing but your column G, right? So if you see, what I'm saying here is this residual, what I'm saying is these are normally distributed. If you see, H2 is nothing but my residual. It's normally distributed with a mean of 0 and has certain standard deviation. Okay. So what happens is, in the MLE method, we'll actually multiply the probabilities, this multiplied by this, multiplied by this, multiplied by this, and so on. But we all know that, these all are in already 4 digits. And if we multiply this, it will become such a large number. But we all know that the beautiful thing about log is what? Log of a times b times c is what? Log of a plus log of b plus log of c. And that's the beautiful mathematical property, right? That if we take log of, see, as I told you, when we have to calculate this sum, what we have to do is we have to multiply each of them. So when we take the PDF, we have to multiply each of them. And so when we'll multiply each of them, the estimator will be very big. It will be very big. And that's why we thought of taking the log distribution instead of doing a times b times c. What we are saying is let's take the log of a times b times c. And what is the log of a times b times c? Log of a plus log of b plus log of c. And that's why we do this. Okay. That's why we do. And that's why we add all of it. If it was just this, we would have multiplied each of the component, but because we have taken log, that's why we are adding all the components because of the mathematical property. So, and that's how we try to calibrate the math parameter using MLE such that we try to maximize this value. So I hope that is clear to everyone. So now let's come to simulation. Okay. So these are the components, calibrated components that we have observed using the MLE method. Now, if you see, this is at time 0, T0, these are the interest rate levels, right? The latest interest rate level is what? 5.52%, or you can say 0.0552. It's the same thing. So at time t equal to 0, these are the interest rates. Always remember, if I talk about industry, in industry we generate like 1,000 simulations, even 10,000 simulations also. So it depends on the use case, But in the Excel spreadsheet, I've just done 10 simulations so that it's easy for all of you to understand. Okay. So the first thing is, what we have to do is we have to use this equation. dRt is equal to A times B minus RT dt plus sigma square root of RT dWt. Okay. The first thing that we have to do is we have to use this equation to simulate the first value. To simulate the first value. So let's understand how I have I simulation. So just remember, this is the DRT term. This is the DRT term, and I'm adding the previous day interest rate to get the current interest rate. Why do I do so? Because if you see what is DRT, DRT is nothing but the change in interest rate. Now when I add the previous day interest rate with the change in interest rate, that will give me today's interest rate, right? That will give me today's interest rate. Or what I can say is, let's say at t equal to 0, I have this value. So if I calculate dr term at dr term here, and then just add this component, that will give me this in this interest rate at level at day 1, right? So let's see how the simulation is done. Let's see how the simulation is done so that it's easy for all of you to understand. So what we'll be doing is we'll be just implementing this formula. Okay. What we'll be doing is we'll be implementing this formula. So if you see, this is B1, which is A, which is the speed of reversion. A times B minus RT. What is RT? Previous day interest rate. Always remember, RT is what? Previous day interest rate. So A times B minus RT dt. What is b6 dt, right? Plus, if you see what is this b3 is nothing but sigma times square root of rt e2 is nothing but the previous day interest rate, times, if you see this equation, what is dwt? Brownian motion, right? Dwt is nothing but dwt is the Brownian motion. And how do we model the Brownian motion? Is square root of, so this is how you model the Brownian motion: square root of time multiplied by random number which is generated using the normal standard distribution. Okay, so random number generated using the normal standard distribution multiplied by the square root of time. That's how you will generate the Brownian motion. So this is a very standard formula of generating Brownian motion, okay, which is the dWt term. So now up till here we have modeled DRT. We have modeled this DRT, and what I'm doing, I'm just adding the previous day interest rate. So the previous day interest rate with the DRT term. So what I'm saying is, okay, I have the previous day interest rate, and I know how much change in the interest rate will happen, and I'm adding both of them to get the next day interest rate, right? So so at t equal to 0, the interest rate is 5.0, you can say 5.52%, and the next day it is 5.51%, right? Okay. So now, and similarly, so this is what we did. Similarly for day two, what we'll do the same thing. We'll do the same thing. We'll use the same formula, which is the DR formula through the CIR model, and then we'll add the previous day interest rate. Similarly, we'll do the same thing again. We'll simulate the interest rates using the CIR model, the DRT term, and then the DRT term will be added to previous day interest rate to to calculate what? To calculate the current day interest rates. Okay. So that's how you will do for one simulation. And similarly, the same formula will be applied for all the simulations. Okay. The same formula will be applied to all the simulation. Now you might be thinking, why, if the formulas are the same, why, and even if we are starting from the same value, why these numbers are different, right? You might be thinking this. This is because of this thing. Let me get this thing. So if you see, okay. So this is a random number generated using the standard normal distribution. This is a random number generated using the standard normal distribution. Now if I am just refreshing it, every time I click enter, I'm getting a new value. Okay. So it basically means that, see, if you see this component, it is giving a random number every time. And that's why these numbers are different. And as I said, why do we use this Brownian motion? To capture the randomness. See, if you see the interest rates, it was 5.25, 5.28, 5.26, 5.29. If we model the 3 month interest rate, there's so much, so much random fluctuations. So what we are saying is this random fluctuations that you see in the interest rates, these are modeled by what? These are modeled by Brownian motion, right? These are modeled by this component, square root of time multiplied by a random number which is generated using the standard normal process. Okay, so that's how it works. That's how we capture the random fluctuation using this method. And then we have this, the DRT equation. So we'll basically, what we are doing is we are modeling the change in interest rate using the CIR equation and adding the previous day interest rate to get the current day interest rate. So like this, we'll be using the same formula to model the interest rates every day. We'll be using the same formula to model the interest rates every day. If you see, and like this, we'll perform how many simulation? 1,000 or even much more than that. Okay. So just for the use case, I have done only 10 simulations so that you understand how CIR model is being implemented in real life. But okay, so that's how you will model the interest rates. Now if I just plot the graph of it, that's how these graphs look like. If I just plot the graph of all the simulation, if you all remember if you all remember what was my if you all remember this B part, which is what? My long term mean. So long term mean is what? 0.0548, which is 5.48%. So you will see that slowly it will. So if you see 5.489, actually this is 5.489. So if you see this is 5.48, somewhere you can say 0.05.4. Let me reduce it. Let's see what we get. Okay, 0.0549. So if you see around 0.0549, which is this part, right? You will see all the interest rate will converge to the long term mean. And this is what CIR was also saying, that all the interest rate, it converges to the long term mean, right? And this is what we also saw, that it actually converges to the long term mean. Now let's play with the model. So I'm just keeping this speed here. Okay, let me keep this speed here. So if you all remember, I was telling something about the speed. If the speed is slow, it starts from 5.52%, right? Because that is what was our interest rate at time zero, right? 5.52%, right? So if you remember this, the latest interest rate that we had is 5.52%, and after this point we are trying to simulate the interest rates. See, if you see, when the speed is slow, when the speed is just 1, it will take time to converge to the long term mean. But let's say if now just look at this graph. Okay, now let's just look at this graph. If interest rate has gone 5, if you see, let's take it as 1. Now let's see 2, 3. So if you see now interest rates, the speed of convergence to the long term mean, which is 5.49%, it's increasing. See, it's going much faster, right? Let me do 10 so that you can see the impact. Now let me do 30. See, it's going at a much faster rate. 40. Let me do 50. Let me do 100. Let me do 80. Right? Now let me do 100. See how fast the interest rate has converged to the long term mean, right? But we know that using the calibrated parameter, or using the MLE method, the parameter is how much? 11, right? Similarly, just think, if I change this value 0.054, or let's say 0.0547. Let's do this. Or let me keep this 0.0549, not 9550, or 5. Yeah. If I keep the long term mean as 0.551, what will happen? See, if you see, it will converge to this interest rate level, which is 5.51%. Now let's see, let's keep it as 1, let's keep it as 10, let's keep it as 100. How fast the interest rate actually converges to the long term level, which is 5.51%. So always remember one thing. Okay, always remember one thing, that this A is nothing but the speed of reversion, and B is nothing but your long-term mean. Okay, B is nothing but your long-term mean. So I'm just copy pasting our calibrated parameters so it's easy for you to give a look. But this is how you do the calibration. So I'll just walk you through. I'll just summarize the all the steps again. So what you do is you download the historical data, calculate the actual, just convert it into decimal forms by dividing it by 100. So the first piece is calculating the returns, right? Which is the today's value divided by yesterday's value minus 1. Once you calculate the return, you calculate the volatility piece, which is nothing but standard deviation dot sample, and you give the returns to get the volatility. Now, what is this? You are, because we know that this CIR equation, we model the change in interest rate, which is the DRT term. So what we'll do is we'll first calculate the actual change in interest rate, and then using the CIR model, we'll calculate the change in interest rate using this equation, which is A times B minus RT dt. As I said, there are two schools of thought. Either you can use the complete equation, but most of the research papers I've seen, they are using the first equation, which is A times B minus RT. Okay, so we have the actual change in interest rates, and we have the model change in interest rate. And why do I say model? Because this is a model using the CIR model. So we have the actual change in interest rate and the model change in interest rate. Now what we are doing is we are calculating the difference. We are saying that, okay, let's calculate what is the difference between the actual change in interest rate and the model change in interest rate. And then we say that this residual, this follows a normal distribution. Okay, this follows a normal distribution with mean of zero. Mean of zero, why? Because we are saying that let's make this residual zero. Let's make the difference between the actual and the model interest rate zero, and it has certain standard deviation, and of course it has certain, and the we are talking about the PDF, probability distribution function, but it's saying CDF. So let's say CDF is false, which automatically means we are talking about PDF. So now we have calculated the PDF. What MLE says, we need to maximize the likelihood estimator. So, we have to calculate the product of all of this, but this will be very computationally expensive. When I say computationally expensive, I do not mean by money, I mean by time. It will take a lot of time to multiply all of this, and to maximize this value. So what we do is we use the concept of log. We know that because we need to do A times B times C times and so on. So what we say is let's take log of it. The log of this will be what? A log of A plus log of B plus log of C and so on, right? So that's what we did. So we did the log of it, we computed the log of it, and then we just took the sum of the log. Now you have to go into the data, you need to go to the solver, maximize this value by changing which parameters, the A, B, and sigma parameters. Okay, changing the A, B, and sigma parameters, and then maximize this value and just add the constraint that A, B, and sigma cannot be negative, and just solve it. And when you do the solve, you'll get the calibrated parameters, and using this calibrated parameters, you'll put it into the equation to simulate the stochastic interest rate. So guys, this was all about the stochastic interest rate modeling using the CIR model. Okay. So I hope you like the session, and if in case you have any doubts, please feel free to post it. Thank you all for joining in.